Right. Let's discuss about some important sections in computer science, which is necessary for the paper. And here I'm going to take, from here and there, because I have taken the photos from the book. So please excuse me for the background noises. Right. So this is about a flow chart, and you can see in the flow chart you have two decisions, right? And this is about nested loops. Nested loop, you can see that the first loop is based on the first condition, second loop is based on the second condition, right? If the first condition is true, then it will check the second condition, and as long as the second condition is true, this loop will continue, which is the outer loop, the inner loop. This is the inner loop. And if the after the inner loop is completed, it will move to the outer loop. That's why when this is false, when the second condition is false, it goes to the outer loop, right? Yeah, so this is a nested loop, right? Now in computer, you know that when you write a program, it has to be ultimately converted into machine code, which is ones and zeros, right? So I'm going to discuss this very briefly because time is very important. So it will be converted into ones and zeros ultimately. And there are two types of languages, high level and low level languages. Basically the high level language is closer to the human language, so it's very easy to use. Less development time, and low level language, as the name says, it's quite closer to the hardware, right? And examples of low level languages are assemblers, and examples of high level languages are interpreters and compilers, right? Now some of the high level languages that we use are C, C++, Pascal, right? And these languages they use, and Java also, they use compilers. And interpreters are used by programs like Python that we use. And they talk about something called abstraction. Now abstraction is here. Since low level languages are quite closer to the hardware, it's mostly hardware dependent. It depends on the hardware architecture, the computer architecture, right? And when you're writing using machine language, ones and zeros, or assembly language, you need to have an idea about the computer architecture, right? But when you are using high level languages, you don't need to know how the computer is going to behave, how the hardware is going to behave, right? How the hardware is going to be utilized. You don't have to worry about that because everything is handled by the programming language. So this is known as abstraction, right? It is abstraction that allows us to ignore the internal details of complex device such as computer, right? So it's something like a nice example they have given. When you turn the steering wheel, you don't need to know how the wheels are turned. That is done for you, right? Okay. So assembly language, it is a symbolic language. It uses some coding system, right? And these codes are not really user friendly for us, whereas in high level language, when you say print, it's going to print. So it's somewhat difficult to use, difficult to remember these codes. And so we have this programs that converts the programming code into the machine code, which are called translators. Examples are assemblers, compilers, interpreters, right? Right. Now if you take the interpreter and compiler, interpreter converts line by line one statement at a time into machine language, whereas compiler converts the whole program code into the machine language. Takes less time, so therefore machine code at the same time takes less time to analyze the source code, but overall program execution time is slow. Yeah, that's because now it takes less time to analyze the source code because it stops when an error is found. But program execution time is slow because it executes line by line. But here um, it takes a large amount of time to analyze the source code because we need to debug. Because all the errors will be listed at the end after compiling, so we need to correct these errors. But execution time is faster here. Interpreter execution time is slow. More memory efficient here, requires more memory because you need to store the compiled file as well, the object code which is run separately. Continuous translating the program until the first error is met, and this makes debugging easy. Debugging means correcting errors, right? And here debugging is not really easy because all the errors will be listed at once, so you need to find out each error and debug, right? An assembler is used on the assembly code to convert into the machine language, right? An assembler translates each instruction in the source code into a single machine code instruction. Right, so this is what we discussed just a while ago. An interpreter checks the errors of a program statement by statement. Right. Compiled languages are normally faster and more efficient than the interpreted languages. That is during execution. Okay, remember, execution, not debugging, right? Systems require high performance, therefore often created as compiled language. Systems that require high performance are using compiled language. On the other hand, interpreted languages are easy to write code. Most interpreted languages have built-in abstraction and extensive libraries that can be used to help program write the code, such as Python. Python is much more easier than a language like Java. Java is a compiled language, Python is an interpreted language. Compiled languages are faster, efficient in execution. Interpreted languages are slow. And compiled languages are difficult to write, whereas interpreted languages are much more easy, right? Okay. Right. Because of the hardware support in these low-level languages, they are mostly used to write, system software such as device drivers, because device drivers directly talk to the input-output devices, right? When writing things like device drivers, it is easy to communicate with the hardware device and IO ports in a low-level language, as not all high-level languages support low-level IO, right? High-level languages have a major advantage over machine and assembly language, as they are similar to language we use everyday life, right? Okay. Understanding machine code on its own is not enough. You need to explore the interaction between the code, database, text files, of data, computer models, website, and this interaction between code and development hardware. Right. That's if you write in machine code and assembly level. Right. Now let's look at binary numbers, and you know that in binary numbers we have two variations, 1 and 0, and a set of binary numbers is called a bit stream, and you are expected to know how to convert binary numbers, binary, and so on. We'll come to that. And this is about binary addition. Yeah, just try out some of these examples that you can see on the screen. This is addition. When you add 1 and 1, it becomes 2. We can't keep 2 because 2 is more than the maximum value that we can have in binary. So 2 is represented as 1 and 0. Two is 1 and 0, so you keep 0 here and take 1 there, and 1 plus 1 is 2 again. You keep 0, take 1 there, again it's 2, 0, 1, 0, 1, right? So you can see that there's a bit overflow, right? So if we were looking at only 4 bits length, now you can have the result is having 5 bits. So that is called bit overflow. Later on we'll be looking at bit overflow. Now there should be another space to store this extra bit, otherwise the answer will be raw. So this is an example of bit overflow. Now if you convert this into denary, you can see the answer is correct. This is 1 2, let me zoom this in. This is 1 to the power 0 1, this is 2 to the power 1 2. So 1 2 4 8, we have 8 4, that's 12, and this is 13, and here we have 3. 1 1 is always 3, right? And then the total is 16. And if you look at this one, this is 1 2 4 8 16, so we have 16 as the answer here. Similarly, if you do the subtraction, you can see 1 minus 1 is 0, and here we need to bring 1 here, we need to borrow 1 here. So when you take this, the value that we bring is 2, just like in denary number system, base 10 number system, 2, and 2 minus 1 is 1, and here it's 0, so it's 0, and this 1 is there, right? Now if you look at the denary equivalent, here we have 13 minus 3 is 10, supposed to be 10, and here if you look at this answer, this is 1 2 4 8 plus 2 is 10. Okay, so try these exercises. Exercise, right? And the bit that we carry forward to the next position is called the carry bit, right? So that's what is shown here. Right, now you know that there are two methods to represent negative numbers in mathematics, but we can use it for binary as well. One is called the signed representation, the other one is unsigned representation. The one is called signed and unsigned representation, the other one is called 2's complement. Now in unsigned an unsigned method is also called sign and magnitude, because one bit is reserved for the sign, which is plus or minus, and the rest of the bits is representing the magnitude, which is the value, right? So although sign and magnitude or 2's complement can be used for both positive and negative numbers, sign and magnitude has a number of problems, so 2's complement is usually the best method. Right, now here you can see in sign and magnitude we take the most significant bit is the bit which is in the highest position, right? That's here. Most significant bit is 0 if the number is positive. Most significant bit is 1 if the number is minus. That's how we represent in sign and magnitude method. So remember, 0 is for positive and 1 is for negative. Right. So here the problem, one of the problems is that if the bits are fixed and if there was an overflow of bits, then there's a problem, right? Because let's say when you are doing an addition, if there's an overflow and there should be a carry bit taken to the next level, and if this bit is reserved for the sign, then there won't be enough space. So that's one problem that we have in sign and magnitude. The other method is called this 2's complement. In 2's complement, it's really easy to do this 2's complement. First, what we do is, now for example, if I want to represent let's say a minus value, so what we do is, first if we need to convert a minus value to 2's complement, we take the positive value and then we convert that into a set of bits. And then if they are using a particular register, like 8-bit register, 4-bit register, whatever, right, we need to make sure that it has enough bits. Okay. For example, let's say I get 101 or something like that, and if I'm using an 8-bit register, now this has only 3 bits, therefore I need to fill the rest of the bits, right, if it is an 8-bit register. So remember that, right? And after that what we do is we convert the bits into its opposite, right? That is, if it is 1, if it is 1, we convert into 0. If it is 0, we convert into 1. So what we do first is we take the positive value, we convert into a binary value, and then we fill the bits to fill the register, and then we start inverting, that is converting 1 to 0 and 0 to 1. And lastly what we do is we add 1 to the result. We add 1 bit to the result, and that's how we get the 2's complement. When you invert, it is called 1's complement. When you add 1, it is called 2's complement.